In this lecture, we're going to continue here with our investigation of linear regression least squares approach. And in this fictional research scenario, here we have a set of data collected on 11 participants. And these data were collected to address the question of whether marijuana is a gateway drug. And one of the criticisms that exists for marijuana usage is that it can provide a conduit for a user to move into uh, other types of drugs. And so to begin that investigation, following the collection of data, the linear regression approach begins that step by examining if a relationship exists to begin with between these two variables. The variables here include the usage of marijuana over the course of 1 month and the use of other drugs over the course of that 1 month among 11 research participants. And once again, to emphasize that these are fictional data, but in this particular study, it was found that the Pearson product moment correlation, the correlation coefficient, was found to be 0.9314. Now, how do we interpret this? Is that we first look for the positive or negative. And so this is obviously a positive value indicating a direct relationship so that those users that report higher levels or more greater occurrences of marijuana usage over the course of the month simultaneously report greater usage of other drugs. And so as one variable increases, the other variable increases. But if you just look at the data here, that's really difficult to imagine, and we'll see the scatter plot on the next slide. And the second item to assess the correlation coefficient is the strength of this. And so here we see that the strength at 0.93, which is a very strong correlation between these two variables. And the most effective way to understand and to view this relationship, of course, is with the scatter plot. So I use Microsoft Excel to not only make the graph, but to also carry out the linear regression analysis. And so here we look at marijuana usage in grams per week. So I mentioned on the previous slide, it was the number of usages per week, but it's actually grams per week versus other drug usage in grams per week. And what we see here is the direct relationship. So as the number of grams per week increases, so does the usage of the other drugs. And I use Microsoft Excel once again to generate the regression equation. And you can see here that the R squared value is 0.8725, which indicates that strong relationship. And the regression equation, the prediction equation, is given by 0.615x minus 3.0678. And note that the slope here is the parameter always paired with the predictor variable x, and the slope rises at a rate of 0.615 grams per week of other drugs per gram of marijuana usage. And if we just stop here, this is a descriptive approach to linear regression because as we generate these key outcome statistics, we have not yet inferred these data back to the population. And that's what the ANOVA approach does. And so once again, I used Microsoft Excel to generate the linear regression analysis, which will return the ANOVA table. So on the left-hand side, here we see the different sources of variation. So if we assume the model is deterministic and perfect, this is the source of variation of the model itself. The reality of the situation, since we're dealing with real data, will give rise to variation due to the residual term that cannot be accounted for. And so the variation due to the model is the generated regression function. So we can clearly see what causes the variation in y. It's the variation in x. But not every data point was on that line of best fit. So the degree of error, or the degree of the residual, as you can see here, reflects that amount of variation that we cannot attribute to the predictor variable. It's not accounted for. So we don't know what's causing this variation in the study because we only had one predictor. And then the total variation is the total of the model and the residual combined. And the degree of that variation is captured by the sum of squares that was summarized on slide 13. Now, the degrees of freedom, as you can see here, we see different values. So the model degrees of freedom is the number assigned to that is based upon how many predictors we have in the model. And because marijuana usage was the only predictor, we have a degree of freedom of 1. We'll say what to do with that in a moment. As we move down to the residual degree of freedom, we see a value of 9, and this is uppercase N, the sample size, subtract the number of coefficients in the model. And so recall that we had two coefficients. We had the A and the B coefficients, and 11 participants in the study subtract 2 gives us a degree of freedom of 9 for the residual term. The total is just simply the sample size. In this case, the sample size was 11, subtract 1. We then move to the variance, or the mean square. So remember back from ANOVA that the term mean square is the same as variance. The only question in ANOVA is which variance are you talking about or calculating? And to generate the mean square, we just simply divide the sum of squares by the associated degrees of freedom. And since this is a 1, we have the same mean square of 914.90. The residual mean square, or the residual variance, you can see is quite a bit smaller because of the larger degrees of freedom. So it's just simply the sum of squares divided by the 9 here, the 133.65 divided by 9, and we get 14.85. And the test statistic, sometimes referred to as the F obtained or F data, is the model variance divided by the residual variance. Remember, the model variance accounts for the variability in the y-axis that is accounted for by the variability in the x-axis. If we assume a deterministic model, that's perfect. But we know that we're dealing with real data, that there is variability that we can't account for. And the relative proportion of that variability is captured by the variance due to that residual term. And so we end up, so the ratio of the variance of the model to the residual is a very, very large F value. So this very large F value would certainly put it on the order of statistical significance if we had set our type 1 error rate at 0.05, or even if we had set it at 0.01. So this large F statistic would certainly reject the null hypothesis and lead us to conclude that the alternative is a plausible explanation for the data, in that the slope is not equal to 0. We take a look at some of these statistics here to illustrate two different ways to calculate the R-squared value, which is the coefficient of determination, which is the key statistic in regression analysis. Remember, the R was the key statistic with correlation, R-squared, the key statistic in regression analysis. So if we take our Pearson value and multiply it by itself, raised to the power of 2, we get 0.8675. I'll touch on this equation here at the bottom shortly. And so the second way to calculate the R-squared value is if we take the sum of squares of the model, so that's the 914, divided by the total. So what we're really looking here is we're calculating a ratio of how much of the total variability in the data. So the variability is accounted for by the ideal situation with the model and the random variation in the data. And so this ratio is examining the proportion of the total variability accounted for by our hypothetical model. And when we calculate that ratio, we get the exact same R-squared value. So in other words, what the R-squared value tells us is if we multiply this value by 100%, or move the decimal place over twice, we end up with 86.75% of the total variability in the data is accounted for by our deterministic model. And that leaves 13.25% of the total variability in the data is accounted for by randomness, that there is no other variable in the study that we can account for that residual variation. So 86.75 is quite a strong relationship between these two data, and these two variables, and we would conclude that there is a strong direct relationship or predictability of marijuana usage to the amount of other drug usage. And we can use the regression function in a very confident manner to predict other data that we don't have. So similar data collected a second time using the exact same methods, we can attempt to use those data to predict the degree to which a person's marijuana usage will be linked to the usage of other drugs. And you'll get a number from that. But what's really important is that that number will not be exact. There will be a degree of variability. And that's what the standard error of the estimate is. So the SEE stands for the standard error of the estimate, and it has values that are the same units as the outcome variable. So what this tells us is that when we make a prediction using the regression equation with new x values, the number we get is a plus minus 3.85 grams per week of other drugs. So if we don't get a point estimate, we get an interval estimate when we use the regression function to predict future events. So this ends this shorter video on the outcome of a linear regression analysis.